Here's an example of a way you might see a slope field tested on the AP test as a multiple choice question. So if I have this slope field diagram that's given, I'm then asked, what is the differential equation that this diagram might have come from? So you could either physically or just in your mind think about, well, if I made a slope field diagram for each one of these differential equations, which one would come closest to matching this? Just a couple things to point out. Their scale, you can see that's x equals 1, x equals 2, y equals 1, y equals 2. So the fact that there's teeny tiny slope segments in between those values means that the input values include ordered pairs that have fractions, that are coordinate fractions, fractions that are coordinates that are fractions. So if you started plugging in 1s and 2s and 3s, you might not get exactly the same picture, but you can get an idea of whether your slope field diagram would match this one. There's another couple of ways that you can approach this. I look at, you can compare the positiveness and the negativeness of the slope to the answer choices here. So for me, when I see x over y, that means make a fraction out of x divided by y. So that means if x and y were both positive, I should have a positive slope. If x and y were both negative, I should also have a positive slope. And if one is positive and one is negative, I should have a negative slope. And I notice here, a couple places I could look, this is quadrant 4 down here. In quadrant 4, x's are always positive, y's are always negative, which means no matter where in that quadrant I pick my point, the quotient, x divided by y, should be negative, which means all my slope pieces should have negative slope. So you can see that some of these go uphill and some are even 0. So I can rule out option D. And you can sort of go through the options and eliminate them one by one. Here's another thing that I like to do. For me, it's easy to spot, easy compared to some of the other options, where there are horizontal line segments. So I see that there's something going on here, and I have a little tiny horizontal line segment sort of along this line. So I could ask myself, horizontal line segment to me means slope is 0. I could ask myself, well, when would each of these possible answers have a 0 slope? So look at this. dy dx equals x squared. No matter what I plug in for x, am I ever going to get a negative answer? No. The only value of x that's going to give me 0 as the slope is if I let x equal 0. So for this guy, I might expect to see horizontal line segments along the y-axis where x is 0, but that's not what's going on here. Other things you could think about. Oh, so let me see about this sort of trail of 0 slopes that I have. dy dx equals natural log of x. So is there something I could plug in for x that would make the slope 0? Well, the natural log of e is 1, so it doesn't help. The natural log of 1 is 0. So I would expect this natural log of x to equal 0 when, let me move me out of the way, when x equals 1. But x equals 1 doesn't describe this sort of trail that we have down here, so I can rule this out. dy dx equals 1 plus x, so 1 plus x should have a slope, dy dx equals 0, whenever x equals negative 1. Well, that means here at x equals negative 1, I would expect to have horizontal slope segments. And that's not what's happening. So check out this last one, which I saved for last on purpose. If I let x plus y y plus x equals 0. Well, when does that happen? That happens when y equals negative x. Well, check out, what do you think the equation of that line is? Those are all the places where x and y's are opposites. That's where I have 0 slopes. So I'm going to conclude that this is my answer. C is my answer. You could make your own slope field diagram for dy dx equals x plus y and see that it matches. Some other things you might notice. You can think about end behavior. That might be helpful. Just notice I already have an answer to this question, but I'll give you some other options for how you could have arrived at that same answer. So it seems to me that if I look up here sort of in this top corner, that tells me that as x gets bigger and y gets bigger, what happens to the slope? It seems to be big and positive. So I would expect, well, this tells me if I'm looking across here, if I look along horizontal lines, are all the slopes the same? Are the slopes all parallel? Are the slope segments parallel? No. And if I look along vertical lines, are the slope segments all parallel? I would say no. So that gives me another hint. I think the differential equation that this diagram comes from must depend on both x and y. Otherwise, if it depended only on x, then we would have parallel slope segments along vertical lines. If the derivative only depended on y, we'd have parallel line segments across the same horizontal line. So now I'm down to choosing between these two. That's another way to think about this problem. All right, here they've asked sort of a different question. They say, here's the slope field diagram. Here's a picture of the differential equation. What do you think is the solution function, the particular solution, or even the general solution? So your technique here is to either come to every one of these solutions, find the derivative, and then make a slope field diagram for that derivative and see which one matches this. Or you can ask yourself, if you're familiar with these functions, which function could I draw into this picture and have it sort of match? Well, can you imagine coming in and graphing y equals x squared? That's not a very good y equals x squared, but that doesn't line up with those little slope pieces. What happens when I try to graph e to the x? Well, here's what e to the x looks like. And I know I can be off by a constant, but I can't run counter to the slope field pieces that are there. So e to the x doesn't fit. E to the negative x is 1 over x. Oh, okay, so that's e to the x, but flipped around the y-axis. So that's not what's going on here. And we have cosine of x. Well, can I draw a cosine function into here? That's 1 and 2. Cosine would look like this. That doesn't match up with the little pieces I have. So think about the natural log function, which looks like this. And you can see that of all the ones we've drawn in, that's the one that comes closest to lining up with the slope field pieces that are already there. So your answer here, y equals natural log of x. And then one last example. Which of the following is a slope field for the differential equation dy dx equals, pretty sure that says x over y. Let me check my copy. That says x over y. The equal sign kind of got smushed together, so it might look like a negative, but that says dy dx equals x over y. So I think in my head, and there's lots of other ways to approach this, I'm looking for a slope field diagram that depends on both x and y. So I'm expecting no parallel line segments across vertical lines or across horizontal lines. Oh, but look, that didn't help me. It didn't narrow down anything. Okay, so now I'm expecting, check this out, x over y. Whenever x and y are both positive, my slope pieces should be positive. So x and y are both positive in quadrant 1. So I'm looking at this graph, and in quadrant 1, I see some of these guys go downhill. Is that answer B? So I'm going to rule out answer B. Similarly, answer D has negative slope segments in quadrant 1? It's not D. Anybody else have negative slope segments in quadrant 1? No. Okay. So I'm expecting that when x and y are both negative, I'll have a negative over a negative. I'll have a positive result. So I'm expecting in quadrant 3, where x and y are both negative, positive slope pieces only. There's some negative ones there. So that's not my answer choice. Let me check out this one down here. Okay, so I'm kind of down to C and E. Let me, oops. Kind of down to C and E. So whenever x and y have opposite signs, when I have a fraction x over y, my slope should be negative. So that tells me that, any positives here? So then something else I can consider, if I have the fraction x over y, I can let x equal 0 and the result will be 0. I can't ever let y equal 0. If I let y equal 0, my slope should be undefined, which means whenever y equals 0, it should look like I have little vertical line segments at y equals 0. So this part here, C, it looks to me like when y equals 0, which is sort of along this axis, I have slope segments that are increasing from 0. But really what I'm expecting is more like what I see here in part D, where near the line y equals 0, this horizontal line, the x-axis, I'm expecting slope segment pieces that are vertical or nearly vertical. So my answer choice here